problems in 3 dimensions. So again, we're going to be using our same trig tools we've got. Just for a quick review, we have the primary trigonometric ratios, which we can use in right angle triangles. Then if we are in acute triangles, we can also, for a right angle triangle, have Pythagorean theorem, a squared plus b squared equals c squared. We also have the sum of interior angles is equal to 180 degrees. Okay. Then when we are in these, this works in any triangle. Then we look to the sine law, which we can write 2 ways. I'll just write it one way. This would be how you would use it if you were finding the side length. It's the comparison of a side length, the ratio of side length, and the sine of its opposite angle is equal to, in each case, for every side of the triangle. And then we have our cosine law, which we can write in 2 ways, but we've got c squared equals a squared plus b squared minus 2ab times the cosine of c, or we could write it as cosine of angle b is equal to a squared plus c squared minus b squared all over 2ac. I purposely used different letters than I usually use in each place. Just so you can see, you can apply this to any side and angle in a triangle as long as you use the correct information in the correct place. So when you're looking for angle B, then you have to remember that you're going to have a squared plus c squared, the 2 adjacent sides, and then you're going to subtract the opposite side length, and down here again is a and b, or sorry, a and c, the 2 adjacent side lengths. Just like here, the key is to remember that if you're looking for side length c, angle c is the only angle involved, and it's way out on the outer side of the equation, and then you've got a and b here and a and b here. So there's no notes for this lesson except for just our examples, so let's dive right into it. We've got example 1, use primary trigonometric ratios to solve a problem in 3 dimensions. So we have a radio antenna. You have the diagram there in front of you already. You have a radio antenna. It lies due north of Sam's house. Sam walks to Alina's house, a distance of 1,200 meters, 50 degrees east of north. So there you have the angle of the triangle that is lying on the ground between the base of the tower to Sam's house to Alina's house. There you have, from Sam's perspective, 50 degrees. From Alina's house, the antenna appears due west. So she's looking straight west at that thing. And has an elevation of 12 degrees. Determine the height of the antenna to the nearest meter. So you can already see, and I can split this into 2 triangles. You can see that your final answer is going to be found by using the triangle that involves Alina's house, and here I'll use A for the base of the tower, and I don't know, T for the top of the tower. Okay, that's going to give you the vertical height of the tower right there. So that's our goal right here, is the H that we're looking for. This is the Alina's house, the base of the tower, and the top of the tower. Okay. The other triangle that we're given information for is the ground level triangle, which has the base of the tower, which we called A, at ground level. And then everything was kind of, this was due north from Sam's house, and the tower was due west from Alina's house. So again, a right angle triangle, and some of the information that we've been given. We have a 50 degree angle, and we have 1,200 meters. So if it's helpful to split your work into 2 triangles like that, here we have the ground level triangle, here we have the vertical triangle from Alina's house to the top of the tower, you can go ahead and do that, okay? I know that they're both right triangles, so we can use our primary trig ratios, SOHCAHTOA, to solve both of these triangles. All right. In order to use the information, in order to solve for this triangle here, where I have 12-degree angle already. I'll write that in. Okay, in order to get the height using this triangle, I need one more piece of information. And it turns out it's going to be this side length, AE, is what I'm going to get in order to use the second triangle, because that's what the two triangles share. Okay, so that's easier to see in the diagram in your notebook. But if two triangles share a side length, then that's going to be the one that we want that we want to solve first. Okay, so here we're going to be looking for AE using the first triangle, then I'll transfer that answer over here, and then we'll find H. So I'm given the angle of 50 degrees, angle S. I have the hypotenuse, and I'm looking for the opposite. Okay? And let's just call that the distance from A to E. Okay, so it is the opposite. We're going to label that side D. I could label it little s since I broke my triangles up into two separate triangles. I could use S, but we're going to let D be the distance from Alina's house to the base of the tower. Let D be the distance from Alina's house to the base of the tower. Alright, well, that is the sine ratio, opposite over hypotenuse. So we're going to go with the sine of angle 50 degrees is equal to D over 1200. All I have to do here to get D by itself is multiply both sides by 1200. So D is equal to 1200 times the sine of 50 degrees, which my calculator will give me approximately 919. This is measured in meters. So now I can go ahead and take that information, AE, and place it here. And now, in order to solve for the height, I'm looking from the perspective of angle E. I'm looking for opposite, and I have adjacent. So here we're going to use the tangent ratio, without a whole bunch of notes. The tangent of angle 12 is H over 919. To isolate H, I just have to multiply both sides by 919. Punch that into my calculator, and you'll get approximately 195. So the height of the tower is approximately 195 meters. Again, if you can do this just by looking at the one diagram that you've been given, that's fine. I broke it up just to show you to separate the triangles out. Look for the shared side. Use one triangle to get the information that you're still missing, and then solve what the question actually asks you to solve, which in this case was the height of the tower. Example 2, you have the diagram there in front of you. I've gone ahead and drawn mine, just so I have something to talk about. A surveyor is on one side of a river. On the other side is a cliff. We do not know the height of the cliff. The surveyor wants to know the height of the cliff. The surveyor lays out a baseline, AB, on the same side of the creek that she's on, same side of the river that she is on. It's 150 meters. From point A, she then selects point C at the base of the cliff and measures CAB to be 51 degrees. We've indicated that in the diagram there. She selects point D on the top of the cliff directly above C and measures an angle of elevation of 32 degrees. She moves to point B and measures the angle CBA as 62 degrees. So a surveyor could actually do this with the tools that they have in order to calculate the height of the cliff just by standing on this side of the river. Okay, they would never have to climb the cliff. They'd never have to go to the base of the cliff. They can take this angle measurement up to the top of the cliff. They can take this angle measurement across the river and this angle measurement also across the river. And from that, they can use the same trig tools that we are using in order to find the actual height of the cliff. So, determine A says determine what needs to be solved in order to actually get the height of the cliff. So we're looking for H, the height of the cliff. What do we need in order to solve for that? Well, it is a right angle triangle. So all we need is our SOHCAHTOA. But what do I need in order, in this triangle here, the tall one, what do I need still in order to use either the sine ratio, the cosine ratio, or the tangent ratio? Well, I have the angle, I just need one other side. So I need either this side length or this side length. Again, our strategy, look for a side length that is used by both triangles. Okay? Because AC here is used by both triangles, that's what we're going to be looking for first. Okay? So A first, find, well, I guess not first, but we're going to, in order to solve for H, we're going to find the distance AC. Okay, well, let's think, what tool am I going to use to find the distance AC? I'm not in a right triangle. I do have a side length of 150 meters, and I have two of the angles, but I don't have any opposite information given. Could I get opposite information? Well, sure, if I know angle A and I know angle B, then I can find out angle C by using the sum of interior angles. And then if I am going to do that, I can use Sine Law, because I'll have C and angle C, and then I'll have angle B, and I'll be able to find side length B. Okay, so we're going to find the distance AC. We're going to use Sine Law to do that, using Sine Law. But first, we need to find the measure of angle C using the sum of interior angles. Now, this is not a super complicated problem, but you can see what we did. We thought about it backwards. We're going for H, so we're going to solve for H. But before we can do that, we need to do this. But before we can do that, we need to do this. So basically, we're going to have 1, then 2, and then your third thing that we're going to do would be solve for H. Okay? So let's start with step 1 here. Determining the height of the cliff. First thing we're going to do, find the measure of angle C by using the sum of interior angles. So this measure of angle C is equal to 180 minus 51 minus 62. So the measure of angle C is 67 degrees. Once we have that, we can now use Sine Law. We're solving for the length B, so I'm going to put that on top of my first ratio over the sine B, and we've just found angle C, so our second ratio is going to be C over the sine of C. Fill in what I know. B is 62 degrees. The side length C is 150 meters. The angle C we just found out is 67 degrees. I can put that in my diagram. And now all I need to do is multiply both sides by the sine of 62. So we have B equals 150 times the sine of 62 degrees all over the sine of 67 degrees. Punch that into our calculator carefully, and you'll find that B is approximately equal to 144 meters. So that's this shared side length here that we just found out. Okay? And now, like we said, we can solve for h using our primary trigonometric ratios. I have a right angle triangle here. I'm looking at it from the perspective of angle A, 32 degrees, and I have adjacent, and I'm looking for opposite. So we're going to use the tangent ratio. Tangent of theta is the ratio op over adjacent. So fill in what we know. We're looking from an angle of 32 degrees, so the tangent of 32 is equal to opposite, which we don't know, over adjacent, which we just found out, 144. Now to solve for h, all I have to do is multiply both sides by 144, which, if I click away gently in my calculator, click, 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 90 meters. Finish with a statement. The height of the cliff is about 90 meters. Now we say about 90 meters, first of all, because some of our answers are rounded. So for instance, the distance b across the river is rounded, and this answer is rounded, 90 meters. But also there's some room for error, margin of error, when you're using these tools to measure long distances. Okay, there you have it. Make sure you do your steps in the right order. Think about what tools you need to use, what you need to find out, and how it's going to be helpful in solving what the question actually asks you to solve, in this case, the height of the cliff. All right, example 3. Justine is flying her hot air balloon. In the diagram, you see her at point J. She reports that her position is over a golf course, G, located halfway between Emerytown, E, and Fosterville, F, at an altitude of 1,500 meters. So all of that is indicated in the diagram on the left. Fosterville is 16 kilometers east of Danburg, and Emerytown is 16.5 kilometers from Danburg in a direction of 42 degrees south of east. So I've taken that information and just on the ground level triangle, ignoring the hot air balloon from Justine, and I drew that here on the right. So this is Fosterville, 16 kilometers east of Danburg. So due east, 16 kilometers. Then from Danburg, you have an angle of 42 degrees south of east in order to get to Emerytown, 16.5 kilometers. Okay? So we have two triangles here, and they work together in order to find what? We need to find the angle of elevation of Justine's balloon as seen from Danburg. So we're looking for this angle, okay, the vertical angle there, and we could draw that triangle too. Don't know if we'll use it, but that triangle looks something like this. Okay, we've got a right angle there. We have Justine up in the sky, the golf course down below, Danburg here, and we have 1,500 meters. And we're looking for this angle. So sure, let's look at that triangle and decide, well, what do we need in order to find that angle? Well, we're in a right angle triangle, so we're going to be using our primary trig ratios. And there's no triangle that shares DJ. So we're not going to use DJ for anything. We're going to find DG. Okay? DG. We're going to find DG in any of my other triangles. I see it over here. Here's DG. Okay? DG is involved in the larger triangle, and it doesn't seem immediately helpful, but we're given the information that G is actually right in between Emeryville and Fosterville. So we know that this length is equal to this length. How does that help us? Take a second to think of a plan. Could we find this length? If we can find the length, the distance from Emerytown to Fosterville, then we could find the distance from E to G. That still doesn't give us enough information to solve directly for DG, but it does give us enough information to solve for the angle E. And once we had that, we could use Sine Law to solve for the side length DG. And then we could go over to this triangle and use that to get the angle of elevation from Danberg to Justine in her hot air balloon. Okay? So there's a bunch of things that happen there. We're just going to walk through it piece by piece. We're going to do what we can do first. So the first thing we're going to do is determine EF. First, determine EF. Well, how are we going to do that? We're looking at this triangle here on the ground, so this is why we drew our second triangle, just ground level triangle. We're going from E to F, and what we have is side, angle, side. We have two sides and the contained angle. I don't have opposite information or any way to get it, so I can't use Sine Law, so we're going to be using Cosine Law. We're going to be looking for the length D, the distance from F to E, and Cosine Law tells us that D squared is equal to our other two legs, the sum of the squares of our other two legs, so F squared plus E squared, minus 2 times F times E times the cosine of capital D, and we have all that information. So F is 16.5, square it. E is 16, square it. 2 times 16.5 times 16 times the cosine of D, which is 42 degrees. Type this into our calculator carefully. Try that on your own. And check the board to see how you've done. 135.87, yada yada yada. But that's D squared, so what do we need to do? We need to take the square root of both sides. We are going to ignore the negative root because we're dealing with a real world distance problem. Distance is always positive, so the negative root is excluded. And we're figuring out here that the distance from E to F is approximately 11.7 kilometers. All right. Now, if EF equals 11.7 kilometers and G bisects EF, then EG from Emerytown to the golf course is 11.7 divided by 2, or 5.85 kilometers. Okay, so I'm going to add that to our diagram here. We've got 5.85. So far, so good. All right. Now what do we have? What are we looking for? Well, again, we don't have enough information to solve for what we want. But if we look over at this triangle, ground level triangle, we have enough information here now with the length EF to solve for angle E. And if we have angle E, then we can certainly get the length DG. So step by step here, we're now looking at this triangle in order to solve for angle E. We have its opposite side length, and we have this guy opposite. Okay, we also have, well, let's just use that. That's the easiest way to go. So we've got the sine of E over 16 kilometers is equal to the sine of D, which is 42 degrees, over 11.7 kilometers. Multiply both sides by 16. 16 times the sine of 42 all over 11.7. Then we take the inverse sine of both sides. So here I'm just going to indicate that by, in your calculator, you're just going to hit the inverse sine of the answer that you get for that. Or you could do all in one step and take the inverse sine of this whole thing, as long as you're good with brackets. You'll find that angle E measures approximately 66 degrees. Maybe I should just box these answers as we go. All the little pieces of things that we have found out. Angle E, 66 degrees. That means this angle E, 66 degrees. And now we can again use cosine law to find out the length of DG, because we have its opposite so we would have three side lengths involved. We have side, angle, side. So we have two side lengths and the contained angle, which means we can find that opposite
Using
side length. Cosine law. Here we go. Leave it down here just to write my equation. I'm working, sorry, it kind of goes up here. And then from there, we're going to go back down here. Okay, cosine law. We're looking for the length dg. So I'm going to call that E. E squared is equal to d, guess I can't use d because I used d over there. So we're going to use EG squared plus DE squared minus 2 times EG times DE times the cosine of angle E. Alright, now I can scroll up, plug in what we know. E squared is equal to, EG was 5.85 squared, DE is 16.5, square that, minus 2 times 5.85 times 16.5 times the cosine of angle E, which we just found out was 66 degrees. Carefully tap, tap, tap it into your calculator. You will get that this whole right side reduces to 227.95. That's an approximate answer. And so the length of E, or the length of DG, maybe it would have just been easier to call it DG. We take the square root of both sides, we ignore the negative root, and we get that the distance between D and G, Danberg and the golf course, is approximately 15.1 kilometers. Now we can head over here into our last triangle. We know DG is 15.1 kilometers. We're looking for the angle measurement of D here. And we have opposite and adjacent. So again, we're looking at the tangent of angle D is 1500 over 15, that's not going to make any sense, is it? 15.1 kilometers converts into 15,100 meters. So you have to convert both to meters, or I could convert both to kilometers and make the numerator 1.5 over 15.1. Doesn't matter which way you do it. Take the inverse tan of both sides. Let's just do it this way. Kilometers. Sorry if you need to erase, but smaller numbers are nice, eh? And we are going to determine here that the measure of angle D is approximately 6 degrees. The angle of elevation from Danberg to the balloon is 6 degrees. Okay, that was long, step by step. You can do it. You're basically saying, okay, I need to find this. What else do I need to know? I need this. Oh, how do I get to know that? Oh, how do I get to know that? And you just go through it step by step, find the things that you need. It's a big problem solving exercise, but I believe in you. You can do it. Practice problems are on page 265, numbers 1 through 7.